Good morning, Kagglers. Well, morning for me. It probably isn't for most of you. Welcome to the Kaggle reading group. So if you're not familiar with the general premise, the idea is that I read a paper for the first time for me, top to bottom. And that's the whole thing. That's the whole thing that we're doing. This week, we're starting a new paper, and it is on NMT. NMT here being neural machine translation, search errors, and model errors. Cat Got Your Tongue. It's by Felix Stolberg and Bill Byrne? Maybe any of those things, from the University of Cambridge, and it looks like Felix Stolberg is now at Google. And this was published at EMNLP 2019 in Hong Kong this November. And the reason that I picked this paper is I ran across a Twitter thread a while ago about it by, let me pull up the thread. Matthias Gallet, pull this up, where he was talking about sort of the contents of the paper and how it has pretty big implications for neural machine translation as a field. And I was like, oh, that sounds pretty cool. I'm going to put this on my list. And it's been on my list for a while now, and I want to read it. So we're reading it. All right, let's kick it off. On NMT, Search Errors and Model Errors, Cat Got Your Tongue by Felix Stolberg and Bill Byrne, I'm going to go with. Abstract. We report on search errors and model errors in neural machine translation, NMT. We present an exact inference procedure for neural sequence models based on a combination of beam search and depth-first search. So they are combining beam search, which is a breadth-first search that I believe we are going to run into again quite a lot in this paper. Hello, Montessor. And depth-first search, so combining breadth and depth first. Wonder what that's going to look like. We use our exact search to find the global best model scores under a transformer-based model for the entire WMT15 English-German test set. It's a machine translation data set. Surprisingly, beam search fails to find these global best model scores in most cases, even with a very large beam size of 100. This is pretty surprising. So beam search is the most commonly used search algorithm for finding candidates to rank generally using the decoder. We'll talk all about that more, I'm imagining. And the idea with beam search is the larger the beam, the more candidates you look at any one time. The more candidates you look at, the more likely you are to find the best candidate. I mean, in theory. So having a very large beam should, in theory, get you better results because you're looking at more potential candidates and there's a higher probability that the best candidate will be in there. So that is pretty surprising. For more than 50% of the sentences, the model in fact assigns the global best score to the empty translation. So I put in a sentence in English and the German I get back is nothing. Revealing a massive failure of neural models in properly accounting for adequacy. We show by constraining search with a minimum translation length that at the root of the problem of empty translations lies an inherent bias towards shorter translation. So they looked at all the candidates and were like, we're not going to look at candidates with a length less than some parameter they passed in. And the results from that suggest that the problem, and the reason why increasing beam search doesn't help is because there's a bias towards very short translations. We conclude that vanilla just means sort of like plain, basic. NMT in its current form requires just the right amount of beam search errors, which, from a modeling perspective, is a highly unsatisfactory conclusion indeed, as the model often prefers an empty translation. So the reason why this is an interesting paper is pretty much everybody uses beam search, and that sort of assumption that a bigger beam will get better results is baked into a lot of NMT, but also other sort of sequence outputs types of NLP tasks. So like parsing uses beam search a lot of times, trying to find the correct parse tree for something. So these are pretty surprising results. All right, introduction. Neural machine translation, some citations for that, assigns the probability P of y given x of the translation y, yj1 in the set of tj, of length j over the target language vocabulary t for a source sentence x in the set of si, of length I over the source language vocabulary s. So the T's and the S's both look funky, but I don't know how to say that with human words. They're big and italic. Via a left to right factorization using the chain rule, which is the same thing as backprop. I'm 80% sure. I was gonna say 90%, but then the more I thought about them, I was like, maybe it's not. I'm pretty sure it's the same thing as backprop. So, Taha, I like your tutorial very much, Rachel. Thank you. Oh, thank you for joining. So the log probability of y given x is the sum of probabilities over j, where j starts as 1 and goes to some sort of maximum length, big J, of the log probabilities of yj, so translation of length j given translations of length j minus 1 and the source sentence. So you generate a bunch of source sentences for various different lengths, and then you find the most probable one. You generate a number of, not source, but target sentences of various lengths, and you pick the most probable one. And Jesper says, backprop is essentially the chain rule. Yeah. I feel like it's one of those relationships that goes some ways, because backprop is the chain rule, but the chain rule isn't always backprop, is my gut feeling. But I'm going to have some coffee, and then maybe I'll have different gut feelings. I've got a little hedgehog mug. Isn't that cute? All right. The task of finding the most likely translation y hat in the set of big T star for a given source sentence x is known as the decoding or inference problem. Y hat is the argmax of P, the P of y given x for y in the set of T, where I believe T is the vocabulary and star is all of the translations. Okay, so all of the possible translations. The NMT search space is vast as it grows exponentially with sequence length. And you can imagine this, so like if you have a sentence, I went to the X, there are a number of different things that I could add with X, so like store, park, library, bowling alley, and then if we increase the sequence lengths, we're not just returning, one word or one phrase, we're returning more things. I could say like, and did something else, but for each of those things, so it's sort of an expanding tree-shaped graph. For example, for a common vocabulary size of T equals 32,000, there are already more possible translations with 20 words or less than atoms in the observable universe, due to the infinitely generative properties of language. Thus, complete enumeration of the search space is impossible, certainly ill-advised. The size of the NMT search space is perhaps the main reason why, besides some preliminary studies, analyzing search errors in NMT has received only limited attention. Because if you're trying to figure out how you got things wrong, you need to look at all the possible ways you could have gotten things wrong, or at least a large slice of them, and if there's an intractably large number of them, then you can't say as much. To the best of our knowledge, none of the previous studies were able to quantify the number of search errors in unconstrained NMT due to the lack of an exact inference scheme, which will be proposed in this paper, that, although too slow for practical MT, guarantees to find the global best model score for analysis purposes. So this is the inference that they're proposing here is not going to probably work super well. For example, during serving the model online, because the latency time is just slow. But if you're sort of figuring out models to then put into production, this could help you learn more. All right. Jesper says, the chain rule is basic math, essentially making differentials of differentials possible. Backprop is performant because of the chain rule, but was done differently before. Helpful. And and thank you, Adnan. In this work, yeah, that's where we were. In this work, we propose such an exact decoding algorithm for NMT that exploits the it's monotonic, so the adjectival form is monotonicity. Monotonicity? Yeah? Yeah. So it's got like one high point. Since the conditional log probabilities in equation 1, here it is, it's numbered on this side, are always negative, partial hypotheses can be safely discarded once their scores drop below the log probability of any complete hypothesis. Okay, so if you have a partial hypothesis and it is less likely than any of the complete hypotheses you have, you can already throw it out. Using our exact inference scheme, we show that beam search does not find the global best model score for more than half of the sentences. However, these search errors paradoxically often prevent the decoder from suffering from a frequent but very serious model error in NMT, namely that the empty hypothesis often gets the global best model score. Our findings suggest a reassessment of the amount of model and search errors in NMT, and we hope that they will spark new efforts in improving NMT modeling capacity, especially in terms of adequacy. Okay, so there's two different things here. So one is generating candidates to rank and pick the best one, and that's the search errors. And then the other one is model errors, and that is once you have your candidates, are you picking the best one for your given translation task? And adequacy here means that the translation you get out is like a good representation of the information that you put in the other language. Perhaps obviously if I have a sentence that I say in English and someone translates it into another language as nothing, like nothing was said, there was no information conveyed, then that's probably not a very adequate translation. All right. 2, exact inference of neural models, and we'll come up to the algorithms once we hit that in the text. Exact inference for neural models. During NMT, equation 2, decoding. So if you remember, we've talked about this a little bit for sequence-to-sequence stuff. So there's usually an encoder and a decoder, and the encoder takes input, like words, and puts them into numbers. And then the decoder takes the numbers and puts them back into words. So BERT, for example, is the encoder half of the transformer architecture. The original transformer architecture, which we also read in the Vaswani paper, has the encoder and a decoder. So decoding is what the decoder does. Is usually tackled with beam search, which is a time-synchronous approximate search algorithm that builds up hypotheses from right to left. Time synchronous. So it's happening in real time. I think that means that multiple candidates are being considered at once. Approximates, you're not guaranteed to get the best answer out. Builds up hypotheses from right to left. So you have your input sequence, which is a language string, which at least in English-speaking countries or English-speaking work, we tend to model is going from right to left, so you start to build out your output in that same direction. Presumably for languages like Arabic, you start from the first position and move to the later positions. A formal algorithm description is given in Algorithm 1. Beam search maintains a set of active hypotheses, H current. In each iteration, all hypotheses in H current that do not end with the end of sentence symbol /s are expanded and collected in H next. The best n items in H next constitute the set of active hypotheses in the next iteration, line 11 in algorithm 1, where n is the beam size. So the beam size is the number of candidates you consider. The algorithm terminates with the best hypotheses when the best hypotheses in H current ends with an end of sentence symbol. Hypotheses are called complete if they end with S and partial if they do not. So let's check algorithm 1. Taha says, how often do you stream? I stream on Wednesdays at this time for the reading group, which I haven't for the last couple Wednesdays just because there was vacation and then I was sick and then we were doing a different event. But usually on Wednesdays at this time, it's the reading group. And then on Fridays at the same time, I do live coding. All right, algorithm 1, beam search. It takes in X, which I believe is the candidate. Let's see, X is the source sentence, okay? And then M is the bean size, and it is in the set of real positive numbers N. I think that's what that means. I'm pretty sure. You couldn't consider negative. You couldn't consider negative candidates. How would that even work? Like someone starts to think about translating something and you're just like, no, stop it. None of that. You have to consider a positive number of candidates. All right, so hcurrent starts with an empty translation prefix and a 0 score. And then for the next, we set it to null. And then for all y in P, where y is translation outputs, we definitely saw y somewhere. There's the y hat. Yeah, so y is a translation, and then P is coming from somewhere. Have we seen any P's previously? Rupchit says, what is beam search? That is. This algorithm is sort of like the technical answer. The helpful answer is that it is a way of ranking, a way of searching for a number of potential candidates in a large candidate pool. The main reason that you would use beam search is when the search space is very large and you are constrained by memory. If I remember, it has been 4 years since I learned about beam search and have used it. Jesper says, aren't natural numbers positive anyway? That sounds right. I don't know what the plus means then. All right. P. What is P? Is P the score for a given thing? When we talk about S. Okay, so lowercase p must be the probability for the current hypothesis, is my guess. So for all outputs, translations, and probabilities in hcurrent. Okay, so that must be the score on a given metric, which here is the log probability. So for all of your candidates, if the next token is the end of the sentence, then you don't put it in next. UP hypotheses ended with S are not expanded. Okay, so you remove it from consideration for the next round of beam search. Otherwise, you calculate the probability given, and also with the W, when W is coming from the next word. Jesper, helpfully. N plus, so this guy up here is natural numbers excluding 0. Okay, that makes sense. So you have to consider at least one candidate. Helpful, thank you. So the union of next and then big U, W from the vocabulary. So you pick a word from the vocabulary and you get the, oh, I see. So you look at every word in the vocabulary and use them as a possible continuation. And then you place your pairs into the current one. Kumar says P, so this P here is log probability of y given x. Okay, helpful. And then that is in algorithm 2. Okay, I see it here. Gotcha. So the default probability is 0, and then we update it if we update it if the next token is not the end of sentence here. So we add to 0 the log probability of the next word given the input, the source sentence and the current translation. All right, and then that's that bit. And then we take the current, so we had the current one, we initialized it empty, we clear out everything in next, and then we populate next for each of the translation candidates in the current one. If the next token is the end of sentence, we're done, we don't expand it. And if the next token is not end of sentence, we look at the log probabilities. We get the log probabilities for each one of the next tokens. And then we take and then we take the n best, where n is the beam size. Yes, where n is the beam size from all of the potential next candidates. And then we take the argmax until everybody is just saying, hey, the next token is going to be the end of sentence, and then we return all of our potential candidates. Okay, so it would be possible for something where the end of sentence to get into the next round if it still ranks highly for this log probability. All right. Robbie says, it looks horrible. How are you reading it? It just takes a while to read math. That's the nature of the genre. All right. So, to reiterate, we start with no hypotheses. We generate a bunch of possible hypotheses. If the next token isn't end of sentence, we generate a bunch of possible tokens. Then we look at all of the tokens that we have, all of the potential candidates we've considered so far. We take the top n, where n is the beam size, and then we repeat again until all of our candidates are like, hey, the next thing is s. /s here is the end of the sentence. And Samuel says, what is /s? So that's the end of the sentence or the output. So you're doing this sentence by sentence. And Jasper says practice. Yeah, practice definitely does help for reading these type of papers. Hello, Anarchy. More coffee. All right. So we talked about pretty much the exact same thing. Hypotheses are called complete if they end with the end of sentence token and partial if they do not. Beam search is the ubiquitous decoding algorithm for NMT, aka everybody uses it, but it is prone to search errors as the number of active hypotheses is limited by n. So this is sort of similar to that thing in genetic algorithms. Genetic algorithms is where you write algorithms using genetic probabilities. Evolutionary things where you have candidates that might be really good 3 generations from now, but they're like stuck in a weird place now, so you don't necessarily consider them going forward. So you don't necessarily get the best result out because you might not get to it because you didn't look at its previous form, if that makes sense. In particular, beam search never compares partial hypotheses of different lengths with each other's. As we will see in later sections, this is one of the main sources of search errors. So partial hypotheses of different lengths. Okay. That makes sense because what we're doing in each round is everything that's not ending in S, we add one token. We add a bunch of different possibilities for the next token. So you can't do it such that you have, here's a good example. So 4 is a very unlikely way to start a sentence, right? But given a large text corpora, 4 and 7 years ago is a pretty likely phrase because it's from a famous speech and it gets used a lot. So if you're just looking at the probability of the word 4 and comparing it to the probability of like the word the is probably going to win and 4 is not going to win, even though the full phrase might be more likely, if that makes sense. So it might be more reasonable to compare 4 and 7 years ago to the, but because those are sentences or partial hypotheses of different lengths, you're not going to get a chance to compare them to each other. All right. However, in many cases, the model score found by beam search is a reasonable approximation to the global best model score. Let gamma? Pretty sure that one's gamma. It sort of looks like a little V written by someone who's feeling fancy. Be the model score found by beam search, P wavy hat? I don't know how to say that either. In line 12, algorithm 1, which is a lower bound on the global best model score, gamma. I'm pretty sure that's a gamma. Is less than or equal to the log probability of y hat given x. Furthermore, since the conditionals log probability of yj given yj minus 1, x, and equation 1 are log probabilities and thus non-positive, expanding a partial hypothesis is guaranteed to result in a lower model score. That meant nothing to me. All right, let's go through that again. Okay, so gamma is the thing that we found, and we know that there's an ideal best model score. So gamma is our current best model score, and we know that there is an ideal best model score, looking at all of the possible candidate translations and all of the possible input sentences, or given the input sentence. The conditionals log p yj minus 1 x, an equation. So the probability of translation of length j given the translation 1 word shorter and the input sentence are log probabilities and thus non-positive. Expanding a partial hypothesis is guaranteed to result in a lower model score. So for all instances of j between 2 and some upper bound, the log probability of, I see. So the probability of a sentence that is 1 word shorter is always going to be greater than the probability of a sentence that is 1 word longer. So what I was saying earlier about 4 and 7 years ago being more likely than 4 is going to always be false under this this modeling. All right, good luck on your exam, Robbie. All right. Consequently, when we are interested in the global best hypothesis, the one hypothesis, y hat, we only need to consider partial hypotheses with scores greater than gamma. In our exact decoding scheme, we transverse the NMT search space in a depth first order, but cut off branches along which the accumulated model score falls below gamma. Okay, so we want to find the best possible translation. So not just sort of like one that kind of works, like the best possible translation. Well, I mean, the question of whether or not there is a single best translation in machine translation in general is, I think, sort of a fraught question. But let's pretend that there is one. We only need to consider partial hypotheses with scores greater than gamma. So if our the partial hypothesis we generate is not better than our current model, global best model score, we can just chuck it out. It's not going to be an improvement because we know that making it longer is just going to make it worse. In our exact decoding scheme, we transverse the NMT search space in a depth first order. So if you have a word and then you add multiple words to it to get a sentence of length 2, and then you get only the top n, and then for each of those you add multiple words to it, so you get a search space of, and then you take only the top n of those, and then you repeat, you're making a tree structure, right? So instead of making the tree very broad, they're going very deep in the tree, and then remove branches where the score they know isn't going to be an improvement to the global model score, so pruning. During depth-first search, we update gamma when we find a better complete hypothesis. So if we find, by going down the tree, oh, hey, this one's really good, this one has a really good model score, that set is the new high watermark, everything that's below that gets cut off. Footnote. Equality in equation 3 is impossible since probabilities are modeled by a neural model via softmax function, which never predicts a probability of exactly 1. So this is why you know that it's always going to decay over time, just like a little bit. Not over time, but over the length of the sequence. So the longer the sequence is, the less probable it's going to be. All right. Algorithm 2 specifies the DFS algorithm formally. Depth first search is what DFS is. An important detail is that elements in T, the set of all possible translations, are ordered such that the loop in line 5 considers the end of sentence token first. This often updates gamma early on and leads to better pruning in subsequent recursive calls. Okay, so when searching, the first thing you ask is, are we done yet? And if you are, then you stop and don't continue to look at that particular branch. So, algorithm 2, I cannot get on the screen at the same time. What if, I think this is gonna mess stuff up. Did that mess it up? Yeah, I think it did. Okay. All right, let's just read it. So our input is X, which is the source sentence. We are given Y, which is the translation. P is in the set of real numbers. It is log probability of Y given X and defaults to 0. Doesn't that have to be negative? Am I just wrong about this being real numbers and also real numbers being positive? I'm just going to Google really quick. Real numbers have to be positive. Match any number you can think of. This includes whole numbers or integers, fractions, rational numbers, and irrational numbers. Can be positive or negative, including the number 0. Okay, it does not. It can be anything. And then gamma is the lower bound, also has to be real. So if the next token is the end of the sentence, then return the translation and the probability, so the score, and then trigger a gamma update, so this lower bound is bumped up. And then Y tilde gets this guy, upside down T? Transpose? I don't know what the upside down T means. Something with an upside down T. We initialize it with a dummy value. And then for all W, which are words in the vocabulary, I believe, P prime is P plus the log probability of W given XY. So we update the probability, and because these are negative, P prime is always going to go down a little bit. If P prime is greater or equal to gamma, then, so P prime is our new one. We do depth first search for X and Y. Oh, we do depth first search with the inputs. Okay, so this is recursive. So if our current probability is greater than our threshold, then we continue going down that particular rabbit hole, given the input sentence, the current translation, and the next word in the translation, and P prime here, so this guy, and also gamma. if we have not improved. So if gamma prime, which we are creating here. Okay, so that's the score returned from the depth first search. So here's the translation. Here's the score. If the score is better than our current high water mark, then we add our translation to this set of translations. Why wavy? I don't think it's called wavy. I don't know what it is called. And then we update gamma to be the current gamma prime. Jesper says, those are real numbers. They're everything except complex. Thank you. And Vinesh says, perpendicular, this guy. Jesper says, is that the dummy variable? Maybe. I don't know where it's coming from. I also don't think it's super important. When I was in grad school, one of my good friends from college was concurrently a math graduate student, and when I was reading papers and I just didn't know what the math was, I'd send him like a phone photo and be like, help me, I can't Google it. There is a very helpful page on Wikipedia, though, that has like a big old list of all of the, not all of the, many of the symbols you might encounter in math and what they mean in people words. All right, so basically we're sort of like going down adding words, and if adding the words we continue to find candidates that are better than our current idea for the best that our candidate could be, we continue to explore that search space. And then at the end we return all of our potential translation candidates and also the score for each of them where they have to be above this lower bound for gamma. Okay, that makes sense to me. An important detail is that we consider as first, we read all that. Exact inference under length constraints. Our admissible pruning criterion based on gamma, and somebody has, Jester says y skiggle, Layla says y tilde, that makes sense. Yeah, let's call it y tilde. And Chen Danieli has offered a link to it, the thing that I was talking about. Yeah, this is the one on Twitch. And here it's list of mathematical symbols on Wikipedia. And you can see it's got, let me zoom out so you can see a little bit better. It's got just like the symbols and some things that they may mean, because many things are overloaded in math, which is great, very user-friendly. All right, exact inference under length constraints. Our admissible pruning criterion based on gamma relies on the fact that a model score of a partial hypothesis is always lower than the score of any of its translation prefixes. Does make a lot of sense why we're getting empty translations back then, huh? Well, this monotonicity condition, I think it's monotonicity, is true for vanilla, or like basic NMT. It does not hold for methods like length normalization, citations, or word rewards. Good, all 2016. I feel like I've read a paper where the first author's name was He, and it was written in 2016, but it was probably a different paper. Length normalization gives an advantage to longer hypotheses by dividing the score by the sentence length, while a word reward directly violates monotonicity as it rewards each word with a positive value. Sorry, I do want to... Okay, yeah, no, I definitely haven't read that. I had a moment where I was not sure myself. Okay, so length normalization tries to get around this returning empty sentences problem by dividing the score by sentence length. Wouldn't that make the score smaller if your sentence was longer? So if I generate a candidate of length 2, then I would divide my score by 2. And if I generate a candidate of length 10, I divide it by 10, and a half is bigger than a tenth? I think there's something that I'm not understanding here. I think I'm advantage to longer hypotheses. Maybe you want the score to be longer, to be shorter? I guess it's, okay, so I guess it's actually giving you the average score per word, if that's your approach. Well, word reward directly violates monotonicity, and each word gets a positive value. So instead of, because log probabilities are negative, instead of always subtracting a little bit from the score, you ensure that you are adding a little bit to the score. In section 4, we show how our exact search can be extended to handle arbitrary length models. Citations. By introducing length-dependent lower bounds, gamma k, and report initial findings on exact search under length normalization. Layla says, what's the score? I believe it is usually the log probability of the whole return translation. Oh, I feel like I read something where people were using Perplexity instead. I can't remember where that was from. This is why you keep a bibliographic database, which I have not been doing for a couple of years now, so you can remember where you read these gosh darn things that you remember in your brain. Yeah, but the score could be, determined by whoever is doing the thing. A little bit more coffee. All right. So introducing length-dependent lower bounds, gamma k, and reported initial findings on exact search, blah, blah, blah. However, despite being of practical use, methods like length normalization and word penalties are rather heuristic, as they do not have any justification from a probabilistic perspective. They also do not generalize as well as without retuning. They often work only for a specific beam size. So this is a parameter that you would tune, a hyperparameter, and it looks like it's coupled to other hyperparameters. So if you change one, you'd have to change the other, which suggests to me that this should be learnable, but also probably extremely expensive to learn. So maybe not a good use of time or compute. It would be much more desirable to fix the length bias in the NMT model itself. Result 3, result without length constraints. We conduct all our experiments in this section on the entire English-German WMT News Test 2015 test set, 2,169 sentences with a transformer base, Viswani et al., model trained with tensor to tensor, Viswani et al. 2018. Did we read this? We definitely read the original Attention is All You Need paper. And this is the 2018. Tensor to Tensor for Neural Machine Translation Core. No, I don't think we have read this. So this might be another paper for us to look at in the future. Scroll. On parallel WMT data excluding paracrawl. Our preprocessing is as described by Stolberg, same first author, et al. 2018a, and includes joint subword segmentation using byte pair encoding, Senrich et al. 2016, with 32K merges. We report cased blue scores, so like uppercase, lowercase, comparable with this thing. What's this thing? matrix.statmt.org. I'm guessing this is going to be a benchmark if it loads. Evaluation matrix, translation, quality of the best systems for test set news test 2019. Okay, so this is what it's being used for. This is using the same metric as this benchmark. Inputs and then outputs. So it looks like a lot of work has been done on English to other languages and less work on other languages to each other, which I think is unfortunately kind of common in NLP. We definitely have an English bias. Note that all right, so 2 here is, where's that footnote from? So this is this footnote from up where they're describing the algorithm. Note that the order in which the for loop of in line 5 of algorithm T2 iterates over T may be important for efficiency, but does not affect the correctness of the algorithm. That makes sense, because if you can find a better candidate earlier on, it means that you can raise your threshold higher, which means that you can kick more stuff out, which means you don't have to evaluate it. And because, it's a growing tree, removing a path evaluation sooner means that you can run much more quickly. But regardless, you're going to see everything. So this is not an approximate search, it is a complete search. I'm pretty sure is the term. It's been a while since I did search algorithms. All right, that makes sense to me. An open source implementation of our exact inference scheme is available in SGMT Decoder, Stolberg et al., 2017-2018b. So you could play around with this if you liked, and this should be, this is a link to the repo for that. Actually, I don't know that it's a repo because it's GitHub.io. Oh wow, there's a whole docs page, a little bit on installation, some tutorials. Very nice. So if no machine translation is something you're interested in, this might be helpful for you if you're looking at model comparison and evaluation. Our main results are shown in Table 1. Greedy and beam search both achieve reasonable BLEU scores, but rely on a high number of search errors to not be affected by serious NMT model error. For 51.8% of the sentences, NMT assigns the global best model score to the empty translation, i.e. a single token, which is not good in terms of being super useful, but I think makes sense given the fact that there's a penalty for longer translations. Jesper says, I can only imagine the reviewers at NeurIPS for non-English to non-English paper. I can too, and it makes me sad. Yeah, hopefully the ACL conferences would be better about that. But yeah, there's definitely a reviewing bias. All right, so here are the what are these called? So here are the results. So as you change algorithms, so greedy search gets you a lot of search errors, but doesn't return any empty results. Beam search with a beam size of 10 gets you also, again, most of your responses are going to have search errors, but you don't get empty results. When you know that you have returned the best candidate, the number of empty results is about half. So in the absence of search errors, NMT often prefers the empty translation, causing a dramatic drop in length ratio and BLEU. And I believe this is the ratio of the input sentence to the output sentence, which in very closely genetically related languages should be more or less 1-to-1. And then for BLEU, higher is better. I actually have a whole blog post about BLEU, but it is a metric. So the fact that you do have search errors is one of the things that makes NMT work, because it prevents you from making modeling errors that because you're not returning candidates that would otherwise be very good. Okay, so if you have a bias towards a certain type of output, say the empty output, and your search is creating errors such that it doesn't return the empty output, then the search errors are correcting for the model errors, is what I'm getting here. Rely on a high number of search errors to not be affected by serious NMT models. A sentence is classified as a search error if the decoder does not find the global best model score. So using the exact search, you know what the best possible score is. If you don't find that, then your best candidate was not in the returned search results. I think. Pretty sure. A little bit more coffee. Figure 1 visualizes the relationship between blue and the number of search errors. Large beam sizes reduce the number of search errors, but the blue score drops because translations are too short. So this is figure 1 here. So this is the beam size, and this is search errors, and this is blue, and this is length ratio. Oh, this is too many axes. I'm having trouble reading this. So blue over the percentage of search errors. Large beam size yields fewer search errors, but the blue score suffers from a length ratio below 1. So I think the search errors and the beam size axes have been manipulated so that they're on the same width. So with a beam size of 2, you get 65% search errors. With a beam size of 10, you get 55-ish % search errors. So the bigger the beam, the fewer search errors, which makes sense because you see more of the space and it returns. There's a higher probability of you returning the best candidate, but you also see an increase in blue up to a beam size of about 10, and then it suddenly drops off. And length ratio, so the length of the returned sentence given the input sentence, slowly drops down as the beam size increase, and this looks monotonic. Interesting. Even a large beam size of 100 produces 53.62% search errors. Figure 2 shows that the beam search effectively reduces search errors with respect to greedy decoding to some degree, but is ineffective in reducing search errors even further. For example, beam 10 yields 15.9% fewer search errors, absolute, than greedy decoding, but beam 100 improves search over slightly, despite being 10 times slower than beam 10, because you're considering 10 times as many candidates. Interesting. Big Don says, do you PC game? I do, but I don't stream it. That's just what I do for fun. One of the things I do for fun. All right, and that's figure 2, which we haven't actually looked at yet. So here is beam search, here is log likelihood. So log likelihood is the score for the top candidate, I'm guessing. So as beam search increases, search errors decrease, log likelihood, so the score increases. The search errors also increase? No. Okay, so this axis is log likelihood. This axis is search errors. Okay, gotcha. So large beams still produce a lot of search errors. I think that would be a little bit clearer here if the axis here was from 0 to 100. But you do see the log likelihood going down, which means gets better because a lower log likelihood is better. Pretty sure. And this is what we're optimizing using, so it makes sense that it goes up. But it doesn't necessarily mean that it's not making modeling errors, because it's not necessarily finding the best result the model could. Let's keep reading. Hopefully that will help me figure this out. The problem of empty translations is also visible in the histogram over length ratios. Figure 3. Beam search, although still slightly too short, follows roughly the reference distribution, but exact search has an isolated peak in 0001 from the empty translations. So let's look at this one. This one's 3. Oh, I see. So the purple here is the actual ratio between the target and the source length in tokens. And the beam 10 is the blue, so those match rather closely. But when you know you're returning the best results, suddenly you get this spike at 0 because there's a preference for empty translations. Chen Danley says, truncated y-axis, double y-axis, Hadley would not be happy. There's pretty strict page limit requirements, so I can appreciate the desire to put a lot of information in a very small space, hence the dense figures. But Big Don says, what does this all mean? You might need a lot of background for that. But basically, this is for machine translation, so automating translation between two languages. And we are looking at, this paper is looking at the ways in which, given an input sentence, you generate the possible outputs, and you figure out which one to pick. And it's showing that the way in which you generate outputs affects whether or not you get a good translation back, basically, is the super high-level view. Sugaru says, the log likelihood is in negative values. As it goes up, the log likelihood becomes more positive. Yeah, so as the beam search increases, the log likelihood increases, but part of that increase is that we get more empty candidates because adding additional words always decreases the log likelihood because we are not using a word reward or length normalization. Yes. Got it. Yes, it's making sense. I'm picking it up. A little bit more coffee. Thank you, Sicarto. All right. Okay. So what we're seeing here is that beam search sure enough does, exact search sure enough does give us empty translations, and the problem is not in the search. We know that the problem is in the modeling. Table 2 demonstrates the problem of search errors and demonstrates that the problems of search errors and empty translations are not specific to the transformer-based model and also occur with other architectures. Even the highly optimized transformer big model from our WMT18 shared task submission has 25.8% empty translation. So over a quarter of all translations returned were just, they said nothing. That's what you get to know. Let's see, that was table 4? Table 2? Table 2. So here are the different models. We have LSTM, long short-term memory, a type of RNN, and lots of search errors and also lots of empty translations returned. And a lower blue score. So blue score is going up as you look at these different models. Search errors are going down, more or less, except for SpliceNet. And the number of totally empty translations is also going down. But again, these models are getting almost half of the translation returned are empty. And here, over a quarter of the translations returned are nothing. So the recurrent LSTM, convolutional SliceNet, Kaiser et al. 2017, and transformer big systems are strong baselines from a WMT18 shared task submission. Figure 4 shows that long source sentences, so if I have a really long text chunk that I'm putting into the translation algorithm, are more affected by both beam search errors and the problem of empty translation. So beam search has more problems, and you're also going to have more empty translations. The global best translation is empty for almost all sentences longer than 40 tokens, green curve. Even without sentences where a model prefers the empty translation, a large amount of search errors remain, blue curve. Figure 4. Figure 4, here we go. So here is the percentage of empty search errors, I believe. Number of search errors under beam 10 and empty global bests over the source sentence length. Okay, so this is the percentage of search errors, and it is a search error when the model does not find the global best minima. Is that what it was? A sentence is classified as a search error if the decoder does not find the global best model score. Okay. So for a sentence under 10 words, relatively few errors, search errors. And then as the size of the sentence increases, the number of search errors go up. These are the search errors. Oh, sorry. So we're doing 3 different percentages on the same graph. Big Don says to allow for real-time translation. So this particular approach that they're talking about here would be more useful for comparing different models before picking which one to use to do real-time translation, because you are guaranteed to find the best candidate, but that means that you probably are going to end up looking at more things, so it's a little bit more slow. It would introduce some more latency. Pranav, anybody published at NIPS? I mean, I would hope that if you are currently in Vancouver, which is where NeurIPS is being held right now, you would be at the conference doing things and not not watching me. I mean, if you're currently at NeurIPS and you're watching me, hi, welcome. Make sure to take breaks. Wash your hands really often. I always get sick at conferences. Yeah, those are my conference suggestions. Okay, so search errors. So all of these things are going up as the source sentence length increases. And I believe the parenthesis here means non-inclusive, so up to but not including. So 20 is not in this bin, but it is in this bin, I believe. So as your sentence lengths go up, your search errors increase. So these are where the model does not find the global minima. The percentage of translations returning empty sentences goes up. So you get to over 50% empty translations, looks like at about 25 words long. And also if you remove the empty translations, search errors do continue to go up, but not as quickly. Even without sentences where the model prefers an empty translation, a large number of search errors remain. So, Pranav says, are you at NeurIPS right now? No. I actually live sort of close to Vancouver, but no, I've got too many things to do. Jesper says, hand sanitizer is golden, also flu shots. Yeah, get your flu shots. Make sure you're doing your best to maintain a healthy community, literally and figuratively. All right, so it's a little bit after 10, and I'm going to wrap that up now. Also, my voice is getting a little bit on the flaky side. So far we have read a little bit over half of this paper. The big problems are that it looks like beam search is almost always not finding the best global minima, but when you do know that you're finding the best global minima, you're also more likely to get empty translations because adding additional words will monotonically decrease the probability of the given output sentence. And there are some methods for adjusting for this, so length normalization, and then a reward for each word, so adding words increases the score, and removing that sort of monotonic decay. And presumably the authors will propose their suggestion in the second half of the paper. And we will read that next Wednesday, starting at the same time, 9 a.m. and 9 a.m. Pacific, I should say, sorry. I should be clear what time zone I mean, which I believe is 5 p.m. GMT and like 10:30 p.m. IST. Yeah. So thank you very much for joining. I hope this was helpful. Chen says, finally got to make it to your stream. Thanks for doing this. It's always nice to hear someone else talk through math/algo notation. I'm glad it's helpful. This is how I learned to read papers. Basically just walking through them with my fellow graduate students. All right. When I was in grad school, I'm not in grad school anymore. I'm a doctor now. All right, thank you for joining, everybody. I will see you on Kaggle and then back on the channel on Friday for a live coding stream. And I think I know what we're going to do, and it's going to be fun. All right, I will see you then. Bye.